All right, I'm going to discuss the two things I haven't really talked about much in class yet. The equations of exponential functions and arithmetic series / sequences. So this first question here, it says circle the exponential function. Hopefully by now you can see that the exponential function is going to be the one on the right, a graph that has x as an exponent. This is the exponential function. So here's a general form of an exponential function equation. You'll have a times b to the x. So the first number a, that's the starting value. B is the growth / decay factor. And then x is the number of, basically, number of units of whatever the input is. So if it's time, the number of, in years, x would be the number of years that have passed. So let's look at how this could practically translate here. So let's say we want to write an equation now. I'll say y equals 2 times 3 raised up to the x. So 2 is in the a position, that's your starting value. So your initial value would be 2. And if this was, you'll see some questions sometimes about money. If it's a money question, the 2 will be the starting value of the account or the principal. Also called the principal. So just be aware of that. And it's also oftentimes a y-intercept. So here 2 would be the y-intercept. So if I graph y equals 2, parentheses 3 to the x, 2 would be the y-intercept. So I'll graph y equals 2, parentheses 3 to the x to show you that 2 is the y-intercept. Maybe 10 billion years later, Desmos will load. Let's see, all right. So 2 parentheses 3 to the x. You can see here, 2 is the y-intercept. So next thing on the list here, I need to show, talk about asymptotes real quick. An asymptote is a line that a graph approaches but does not touch as it moves away from the origin. So exponential functions have horizontal asymptotes, oftentimes at y equals 0. So that means it will get close, the function will get close to 0, but it won't equal 0. So for example, the function that we just graphed, it starts, here it's at 2, now it's at 1-ish, now it's at 0.0169 on the y, the vertical. And it just keeps getting smaller and smaller, but it won't equal 0. Well, here it's saying 0, but that's probably just an approximation. So when there's an asymptote, it's not going to actually equal 0. So here, it's rounding the answer to 0, but it's not actually equal to 0. So there's a horizontal asymptote at y equals 0. And that's usually what it is for most functions, this blue line. It won't actually touch 0. It'll get very close to it. So let's look at this in the context of a problem. Number 8, the graph of an exponential function is shown on the grid, which dashed line is an asymptote for the graph. So it's an exponential function, that means it'll be a horizontal line. So eliminate answer choice Q and R. No way, Jose. So we are looking at now, let's see. Stylus. So we're looking at a horizontal line, so it can either be S or T. And which line does it appear to approach but not touch? That's going to be right here. It's approaching this, whatever this value is, but it's not going to actually touch it, because there's an asymptote there, wherever this S is. So the answer is line S. The answer is line S on this one. All right, number 31, a student used f of x to equals 5 times 1.012 x to the x to show how the balance in a savings account will increase over time. What does a 5 represent? So this refers to something I said a second ago. So look at this general form here. It says, what does 5 represent? So I'm going to highlight this 5. The 5 is right here. It's this first number in front, so it represents A, and A represents our starting value. So we start with $5 in the bank. So based on that, the answer choice is D, the starting balance of the savings account. You start with $5. That's what that 5 represents. All right, and now that that's all I want to say about exponential functions, and now I want to quickly touch on sequences, arithmetic sequences. They are a bunch of numbers in order where you just add one number to continue the sequence. So here, there's 3, 5, 7, and 9. You can see that they're adding 2 every single time. So 3 plus 2 is 5, 5 plus 2 is 7, 7 plus 2 is 9, etc. So we have a sequence right here. So sequences can be described using this formula below. A to the n equals a to the 1 plus parentheses n minus 1 times d. This looks confusing when you first see it, but I'm going to break it down. So a to the n is the whatever term you're looking for. If you want to know the first number, it would be a to the 1. The second is a to the 2. Third, a to the 3. The 50th is a to the 50. A to the 1 is the first term. So here the first term is 3. So the a to the 1 in this case would be 3. So let me highlight that. So here a to the 1 equals 3, the initial value. And then n minus 1. So don't worry, get caught up in the n minus 1. That's, n is how many, whichever number you want. If you want the 30th number in the sequence, you'd put n as 30. D is the value that it increases every time or decreases. So this 3 plus 2 equals 5, 5 plus 2 equals 7, 7 plus 2 is 9. So it's going up by 2. So here D equals 2. So if you wanted to use this equation for this problem, it would be a to the n equals 3 plus n minus 1 times 2. So that would be the equation for this one. And now you can use it to find any term. Let's say you want to find the 30th term. What's the 30th number in the sequence? So the 30th, that means we're going to plug in 30 for n into our equation that we wrote below. So a to the 30 equals 3 plus, we're going to plug in 30 for n, 30 minus 1 times 2. So a to the 30 equals 3 plus 29. That's 30 minus 1 is 29 times 2. We can put this in the calculator. 29 times 2 plus 3. 29 times 2 plus 3 equals 61. So the 30th term in the sequence is 61. So a to the 30th term is 61. That's how a sequence works. We'll now use that information to solve this star problem. Sequence can be generated by using a to the n equals 4 times a to the n minus 1, where a1 equals 6, n is a whole number greater than 1. What are the first 4 terms in the sequence? The first thing I'm going to highlight is the most easy to understand. A to the 1 equals 6. Remember, a to the 1 is the first term. So 6 is the first number. Now we need to find, what are the other numbers? What's the second number when n equals 2? We found when n equals 1, that's the first term. What about the second term, third term, fourth term? So we're just going to use the equation that was given. It says a to the n equals 4, a to the n minus 1. And remember, n is the number of terms, or the number of terms in the sequence that you want to find. So we found the first term is 6. We want the second. So we're going to find a to the 2. Well, that would be, we're just going to plug in 2 for n in the equation. So 4a to the, we're plugging in 2 again, so 2 minus 1. Well, 2 minus 1 is just 1. So a to the 2, the second term of the sequence, is 4 times a to the 1. And what is a to the 1? They told us a to the 1 is 6. 6. So on the bottom here, a to the 2 is just 4 times 6, which is 24. So our second term is 24. To find our third term, we would just plug in 3 for n. So we would get, I'll do it in green, a to the 3 equals 4 a sub n minus 1. And for n we have 3. So 3 minus 1. 3 minus 1. 4 times a to the 3 minus 1. A to the 3 minus 1. Well, 3 minus 1 is 2. So 4 times a to the 2. So the third term is 4 times the second term. The second term was 24, remember? So the third term in our sequence is 4 times 24. So 4 times 24 equals 96. So you can start to see our answer here. The only answer choice that matches is F. I'm not going to bother with the fourth term, but our answer choice is F on this one. So that's how you would solve using arithmetic sequence. And that's it. Now I've really taught you everything. You geniuses can go forth and master all of your algebra. And I'll end it there. So sorry, people, you're about to get kicked off the Zoom, and I'll restart it in a second.